Emergency stop! Get out of my way. A car drives 40 meters per second when a cow crosses the road up ahead. It takes the driver 1.5 seconds to realize the hazard and move his foot from gas to brake. Then, with the brakes fully applied, the car decelerates at a rate of 8 meters per second squared. How far does the car travel during this entire sequence? First, we're going to fill in everything that we know. We know that the initial position and time are both 0. The speed at the beginning and end of the first segment is 40 meters per second because the car does not begin braking yet. The time for the first segment is 1.5 seconds because that's how long it took the driver to react. This is your reaction time, or sometimes it's known as thinking time. It's the time it takes to say, uh-oh, gotta stop, and then the neurons firing in your brain telling your body to move those muscles from the gas to the brake. The acceleration of the first segment is 0 for constant velocity. That's going to be the part that trips up everybody. Not everybody, but the careless student will get tripped up by that. And the acceleration for the second segment is negative 8 meters per second squared because we're moving forward and we're slowing down. Then the final velocity is 0. So taking all of that and plugging it in. We can get the distance for the first segment using our displacement formula, where average velocity is 40 meters per second, the average of 40 and 40. To get a displacement of 60 meters, add this to the initial position to get the final position at the end of the first segment. Don't forget to add that. This means then we can use acceleration equals our change in velocity over change in time to get the time interval for the second segment, which is a equals blah, 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 blah. This means that it takes 6.5 seconds to come to a full stop. We again use our displacement formula with average velocity to get the distance of the second segment, where the average velocity is 20 meters per second, the average of 40 and 0. So 40 plus 0 divided by 2 gives us 20. Plugging it into our displacement formula, we get our displacement of 100 meters. Now we'll add that to the 60 meters already traveled to get 160 meters total to stop, which answers the question. So this type of question probably wouldn't be this forward. Instead, it would say there's an animal 140 feet away. Is the animal's life spared, or something similar to that? In which case the answer to this would be no. Just make sure that you're answering the actual question. Going through all of these steps is great, but make sure you know what the question is specifically asking you. For this one, it's only how far does the car travel, so we're good. Our narrative: at a constant 40 meters per second for 1.5 seconds, the car travels 60 meters before the brakes are applied. According to our displacement with average velocity, then the car takes 5 seconds to stop with its negative 8 meters per second squared acceleration. Using A equals delta V over delta T, now the average speed during those 5 seconds is 20 meters per second, which is the average of 40 and 0. So using delta X equals V times delta T, the car travels 100 meters while braking. Together, this makes 160 meters of total stopping distance. Here are the 3 graphs. The first segment is shown in blue, where the car travels 60 meters in 1.5 seconds. No acceleration, constant velocity. The second segment is shown in red. We know our acceleration is negative. We're slowing down. Our velocity is getting closer and closer to negative velocities. So that means negative acceleration, which means our slope up here is tapering to 0. That's it. Come on.